Hello everyone, welcome, and according to where you are in the world, good morning, good afternoon, good evening. This is the latest in a series of global webinars organised and sponsored by the Eye on Earth Alliance. My name is Derek Gludden and I am the organiser and host for today's webinar. I work for the Environment Agency of Abu Dhabi, one of the founder members of the Eye on Earth movement, and I'm speaking to you from Abu Dhabi in the United Arab Emirates. Eye on Earth is a global movement launched in 2011. Eye on Earth's mission is to enable stronger integration of the environment in the Sustainable Development Agenda by enabling all stakeholders to have the data, information and knowledge they need. Guided by a suite of 14 principles, which are aligned with and derived largely from Principle 10 of the Rio Declaration, Eye on Earth is about facilitating knowledge exchange within and between specializations and geographies. The Eye on Earth movement has two main components. First, a convening and governing partnership of some of the foremost data and information focused organizations in the environmental dimension of sustainable development. And they are in alphabetical order: the Group on Earth Observations, the Intergovernmental Group on Earth Observations, GEO, the International Union for the Conservation of Nature, the IUCN, United Nations Environment, the World Resources Institute, WRI, and my employer, the Environment Agency of Abu Dhabi in the United Arab Emirates, to whom a special word of thanks is extended for providing the staff time and the enabling technology for this webinar series. The second and core component of Eye on Earth is yourselves, a multidisciplinary, truly global community of experts who are defined by a shared passion for the Eye on Earth mission, vision, and principles. The magnitude and diversity of our knowledge within the Eye on Earth community is demonstrated by the number and distribution of people who have registered for today's webinar. Just have a look at the map, please. You are, at last count, slightly over 310 people from nearly 80 different countries, and you represent every part of the globe. Whether you are attending live or if you're watching afterwards, welcome. My very great pleasure and privilege to introduce our distinguished speaker, Dr. StuartMinchin. Stuart is Chief of the Environmental Geoscience Division of Geoscience Australia.
Thanks very much, Derek, and welcome to everyone. I wanted to start this webinar by focusing on the opportunities that are in front of us with Open Data Cube. And I'm going to explain a bit about what Open Data Cube is and the experience we've had in Australia of applying this on a continental scale across the entire continent of Australia. And the way I'm going to tackle this is first up to show you a case study of all of the interesting and exciting things we've been able to do in Australia in applying the Open Data Cube capability to the Australian continent. But as I do that, I want you to bear in mind that every product, every data set, every insight that you will see that we are able to glean in Australia is actually globally applicable and can be done for your country through the application of Open Data Cube. I'm then going to talk a little bit about the detail of where Open Data Cube is already being implemented and outside of Australia, and what you can do to engage with that. So without further ado, I'm going to move into a bit of background about our journey in Australia with implementing Open Data Cube. So first, a bit of context. Our planet has been measured from satellite for the last 40 odd years. And in Australia, we've been responsible for collecting that information. My agency, Geoscience Australia, has been collecting Landsat data from the Landsat missions for the last 40 years using a ground station in the centre of Australia at Alice Springs. The challenge that we had in Australia, though, is we'd been collecting this data for many years, but we hadn't been making good use of the information. And that was because it's actually really difficult to turn raw satellite imagery into actionable information for people that are not scientists themselves. Why is it so hard? It's so hard because your raw satellite imagery needs to be tied to the surface of the planet. It needs to be corrected for different view angles, orthorectified. It needs to be calibrated for the fact that one satellite image may be taken in the morning with the sun shining from the east. The next image may be taken in the afternoon with the sunlight shining from the west, with different shadows, different illuminations. Clouds impact very regularly, so you've got to actually remove clouds from your imagery. And these are big challenges to do in a consistent and automated way. If you can do that, though, you can then think about stacking those images up through time and looking at how changes have occurred on the surface of the planet. On the right-hand side of this diagram, I'm showing 4 images that have been lined up to align with where I am in Australia, in Canberra. It's relatively easy to do that with 4 images over a relatively short period of time. But what we found in Australia is that doing that over a 40-year period, we had to correct for the fact that the entire continent had shifted by more than 2 meters over that time. So the same image you're looking at today is not looking at the same piece of land as it was 40 years ago. So you've got to do all of these quite difficult corrections to turn the information, the data, into what we call analysis-ready data. So this is correcting, calibrating, orthorectifying, atmospherically correcting, and cloud removal, that then turns that data into something that you can actually use to look at changes in the environment. Let me show you this, this little video here, which is a video of raw imagery coming from the European Sentinel-2 mission. What you can see from hopefully a series of images is that the images look quite different over time. Some are dark, some are light. Many of them have clouds associated with them, and it's very difficult to pick out any changes that are happening on the surface of the Earth because the artifacts, the clouds, the corrections haven't been done. What we do in the data cube in Digital Earth Australia is we actually correct for all of those issues. And what you're now seeing, hopefully, in front of you is a corrected view of exactly those scenes where all the clouds have been removed, and you will see 3 arrows pointing at key areas where there is change occurring in this, this video. It's very easy to see the changes occurring when you've been able to calibrate, orthorectify, and correct those images. And that is really the power that the data cube provides. So what we have done in Australia is turn these regular overpasses of satellite into dense temporal stacks of imagery where you can look at any individual pixel through the last 40 years of history, or you can do an analysis across the entire continent looking for water, vegetation change. You can look for greenness of vegetation, bare soil. You can look at the coastline and how that's changed. Pretty much anything that you can see with your eyes, you can actually design an algorithm to map across the entire continent at very fine resolution. The picture you're seeing in front of you at the moment is the first product that we generated from the data cube, the Open Data Cube for Australia. And it's a product we call Water Observations from Space. And it's a map of how often we have seen water across the Australian continent at every 25 metres square. And the map you are looking at shows you areas that have been wet quite often over that period look blue or green, and areas that have been wet only a few times look red or orange. So this product, Water Observations from Space, which I've mentioned, was a really significant product for us. We did it actually to measure flood risk across the Australian continent because we didn't have any ability to tell people outside of where detailed urban area studies, engineering studies have been done. what the flood risk people were facing was. So this opportunity to measure this using the satellite imagery was a real boon for us. So this product, a few numbers here, it now covers a 29-year period. It's at 25-metre resolution, so you can actually zoom right in fine detail anywhere in the continent. The information product used data from 300,000 individual satellite scenes. So to give you some context, a couple of things about this. If you were downloading that from the USGS Landsat archive over the internet, it would take you close to 20 years to download that number of satellite scenes. That would be before you did the actual analysis. The second thing to note is that a big change occurred in Earth observation in 2008 when the US agreed to stop charging for the Landsat data. Because prior to that point, in Australia, we used to have to pay 1,000 Australian dollars per Landsat scene. So this product would have cost us $300 million to generate. Instead, through the generosity of the US, through the Intergovernmental Group on Earth Observations activity around making data free and open, we've actually been able to generate this product free of charge. And this enables us to actually make it available to all Australians for their information and use. One other thing to note here is that I mentioned that it would take you 20 years to download this information using traditional mechanisms. It would also take you about 5 years to process. And we can generate this product, which goes back for nearly 30 years over the entire continent at 25-metre resolution. And we can generate that in 3 hours now using this capability. So it's a real game changer in terms of the ability to do these sorts of analyses at scale, at the scale of a continent, but then to be able to drill into that at very fine resolution. So let's have a look at this product. This is zooming in to an area of Queensland, one of our states. And what you're looking at here, zoomed in, is the product of water observations from space. And what you can see here is an area where there is a cotton farm. The green area, you can see some fields marked out there, are actually water storages that have been built to capture the floodwaters running down this river system so that the surrounding fields can be irrigated during the summer to grow cotton. What you'll see is that some of the areas are blue because they have water for most of the period. Some of them are green, so they've had water some of the time over that 30-year period. And there is a lot of area that is red or yellow, so it has only had water a few times. These are the natural floodplains. These are the places that might only flood once every 10 years. But they're easy to see in this product because we've been looking at it for the last 30 years in a consistent way. What we can actually do, because we've got this at 25-metre resolution, is you can click on any part of Australia, any pixel at 25 metres, and you can see how often we have observed that location. So in this case, I've clicked on a pixel in the green area. And what you can see is that we have observed that pixel clearly over that 30-year period 527 times. So 527 times a satellite overpass has come across, and we have not had, it's not been obscured by cloud. However, 87 of those times we've detected water. So only about 16% of the time has the water been in that location. We can then even look at when during that 30-year period we have seen water. So what you see here is a graph of time in the X dimension, and the red traces are no water, the blue traces are water. And what you can see in around 1990, there was a wet period. That would have been when there was a natural flood in that location. Again in 1996, and then in 2010, it goes very wet. that's when they actually built that water storage. So here we have a picture not only of the risk of flooding for every piece of Australia at 25-metre resolution, but we can tell you when water storages have been built, how often they have been filled over that period of time, and how often wetlands have been inundated, and what the pattern of inundation has been over that entire period. So this is a very powerful tool, and it gives us a real insight into water across the continent. We can even connect this to our traditional methods for measuring water. So stream hydrographs are our stream gauges, are our traditional method for measuring water. The problem with stream gauges is they only measure water in one location at a point in a river. And you get a wonderful time series, but you don't have any understanding of what the spatial impact of that water is. Sorry, let me go back to that. So what we are able to do is connect any stream hydrograph within the country to the collection of satellite images and show you in the red dots where those discharge values are matched with a satellite image that covers that point in time. And we can then explore those satellite images to show what that extent of that water was at different points of the hydrograph. So here we are looking at the red dot is in the left-hand picture is the location of the stream gauge. But what you can see around that is a large area of inundation where those flood waters have actually flooded areas. And we can continue to explore and look at how different levels of that stream hydrograph actually correspond to different areas of inundation. And we can generate this for every single stream gauge in the continent. So this is a hugely powerful connection of temporal information at one location from the stream gauges to the spatial information that is generated from the satellite images, telling us about water across the landscape and flood risk. So in future, rather than just receiving a flood warning, telling the local community that the stream gauge at the Diamantina River at Birdsville, in this case, is expected to peak at 10 metres, we'll actually be able to tell them what areas are likely to be inundated from that flood. So this is a really powerful change, a really powerful combination of information. We can even look at it through a flow duration curve lens for those hydrologists online. So you can actually explore the different levels of the flow duration curve. Okay, so that's really powerful, but what we didn't realise that we had done in developing this tool was inadvertently we had created a tool for coastal change detection. Let me explain why. So all of the stuff I've showed you to date is looking at the presence or absence of water. Presence or absence of water happens with every tidal cycle in the coast. So what you can actually do is look around the coastline at areas that are sometimes water and sometimes land. And that is really the intertidal zone. So we can look, for example, in the left-hand picture, we look at the sandbar that's appearing next to this picture of an island. You can see that sometimes it looks like land and sometimes it looks like water because the tide is either in or out. But what's really interesting is these yellow pixels go from always looking like land to always looking like water. And that's coastal erosion at work. And these green pixels go from always looking like water to always looking like land. And that's coastal deposition happening. So here we've created a tool that can tell us what the changes have been to the Australian coastline over the last 30 years, objectively, measurably, and demonstrably. So we can actually generate statistics. We can tell you exactly what changes have occurred across the entire coastline of a continent, all from this one product out of the data cube. You can actually generate animations, so we can actually see that change occurring. And here's an animation showing 1987 through to 2015, and you can see the sand being deposited onto the point on that island, and erosion happening on the bottom end of that island as well. So you can not only generate the numbers, you can actually show your stakeholders the action actually occurring. We've generated for the entire coastline of Australia, a change measure. So this is the area outside of Perth, which is one of our major cities on the west coast of Australia. And what we can do is, if I flick to this view, you can see in red and yellow the areas that have changed over that 30 years. Up in the top end of the screen is where there's a port redevelopment, where there's been reclamation of land. In the bottom end of the picture, you can see a red area where there's been a marina built. And in the middle, you can see a beach that's eroding. So we have this product for every piece of the Australian coastline, and it's all generated automatically through the data cube capability. We've also been able to look at the frequency with which we've seen water into the intertidal zone, and we've turned that into an intertidal bathymetry map. So if you think about it, the deeper the water is, the more often it's wet by the tide. The shallower the water is, the less often it's wet by the tide. So you can look at the frequency with which you've seen water in any given pixel and map that to a bathymetry map of the intertidal zone. And we've now completed that map for the entire coastline of Australia, which has given us unprecedented understanding about how our coast operates, is changing, where there are biological communities of importance. A key biological community, of course, is mangroves. And here is an example of how we've used this tool to actually map mangroves. On the left-hand side of the picture, the two on the left are generated from our data cube. It's a map of mangrove extent and detail. On the right-hand side is the result for the same area of a detailed aerial survey with lots of ground truthing. And we are able to get 87% accuracy from the data cube with zero ground truthing when these comparisons are done. So these products, just to remind you, are available through the Open Data Cube and could be applied to your country. Okay, here's a great example where what this has enabled us to do is not only apply our own algorithms, but to learn and apply other people's algorithms to this same information. So this is a great example where there was great research done by the remote sensing group at the University of Queensland, along with the Queensland government and the Turn facility, to develop an algorithm looking at what we call fractional cover, which is the percentage of green vegetation, dry vegetation or woody vegetation, and bare soil in any given pixel. What we're going to look at here is this field in the center of the screen marked in black. What you're going to see along the bottom of the screen is the percentage of these parameters that appear in that field over time, over the last 30 years. So let's look at the animation. Okay, so what you're seeing here is a pattern of annual cropping, where there is a crop planted, it greens up, it gets harvested, and the next year a crop is planted, it greens up, it gets harvested. So this is the wheat crop along the first few years. What you can see is some years are more vigorous than others, the crop's more vigorous. And then in 2004, there's a big change. And what happens there is that this field is planted with almond trees. So it changes its pattern from an annual wheat crop to an almond plantation. And you can see that it doesn't go back to bare soil at any point now. And in fact, it loses its leaves, loses its greenness in winter because it's now a deciduous tree crop. So this is the entire history of this one field in the center of this farm. But we can generate this for every single field in the country, every single field on the continent. And this can be used to inform the farmers about how their crop's going this year. It can be used to understand what the wheat crop will be, and the yield from the wheat crop will be from this region over time. And we're even seeing the emergence of startup companies in Australia who are taking this information and turning what is a generic measure of fractional cover into a tool for farmers to make decisions about how they stock their paddocks, how many cattle they put in, how many sheep, and turning that into real tools to enable farmers to actually make decisions on the land. Okay, so you've now seen an algorithm that looks for presence or absence of water, and you've seen an algorithm that looks for fractional cover. So here's one that looks at water quality. So this is actually very close to my home. I'm actually talking to you from up near the L in this slide. But this is a lake at the centre of our city here in Canberra. And what you can see at the upper end of the lake is actually going to appear on the right-hand side of this graph. And the lower end of the lake is going to appear on the left-hand side of the graph. And what we've done is lined up each pixel along this graph on the x-axis from the top end of the lake to the bottom end of the lake. And the y-axis is time. And in the colour is the water quality. Red is bad, blue is good. And let's have a look at what's happened to this lake over the last 30 years. So what you can see is from the 1980s through to the early 2000s, quite poor water quality all the way down the length of the lake, very muddy water. But in about 2000, that picture changes and there's much cleaner water from that point forward. So what happened at this point to change this? Well, there were three things that happened. There was an activity to clean up the catchments, to improve the inflows to this lake through capturing stormwater in wetlands and cleaning up the amount of sediment flowing into the lake. Secondly, upstream of this lake, there was a sewage treatment plant, which was upgraded at this time. And thirdly, there was a drought during this period that actually reduced inflows. But what you're really seeing here is the impact of policy. It's telling you what's happening to water quality in this lake. And we can generate this for every single lake on the continent. So you don't have to go out and dip your bottle in the water anymore. You can actually do this remotely and use this to guide where you might want to go and do specific investigations on certain water bodies. But we can generate this for every water body on the continent. Now, there's a sustainable development goal on water quality. How powerful would it be to be able to do this for every water body in the world? Okay, here's another example of a different algorithm. This is looking at fire management practices in the north of Australia. So we have, as part of our carbon abatement actions within Australia, it was recognised that much of our carbon loss to the atmosphere was actually caused by the burning of our tropical savanna each summer. What happens is the savanna dries out and then lightning strikes occur and very intense fires happen during the dry season. So you can see from June to September, some very intense fires. Each one of these dots is actually generated by our data cube. What we do in Australia now is we actually pay our Indigenous community to light the fires earlier in the season when it's cooler. They burn less intensely and they release less carbon to the atmosphere. But the question was this policy actually having an impact? So this is the picture prior to the policy being implemented. And let's have a look at what happened after that policy was implemented. What you can see in blue is the post-policy data, and you can see very clearly that that peak of fire intensity has shifted earlier in the season and it's been lowered. And that's allowing our Indigenous community to claim carbon credits and to generate income for the management of the land. Okay, this is just one that I threw in for Derek's benefit because I found out a few years ago that in Queensland, we actually mine sand to sell to the Middle East. ironically, apparently our sand is better for building buildings with. But this is a map of sand mining occurring in the Moreton Bay area. You can see those snakes of the sand mine progressing, shipping that sand over to the Middle East. But what you can also see is how the rehabilitation occurs after that mine has passed, and where those early mines where you can't actually see any impact on the vegetation or the environment once that's gone past. So it's just as important to be able to demonstrate good environmental management as it is to be able to pick out difficult or poor environmental management, and this gives you the tool to do both. So really important for government. It helps us to target investment. It will help us to report on the Sustainable Development Goals. It will help us in monitoring the health of the environment. But it's also a real opportunity for industry, for people in the agriculture area, farmers, and the spatial area, the mining sector, aquaculture. All of these industries can benefit from the use of this information. And they don't have to become remote sensing experts to do this, because the data cube turns this data into actionable information that's of importance and understandable to these communities. So in Australia, we've prototyped all of these issues for the data cube, and that, it's a long list and it's a growing list. Pretty much anything that you can observe with your eyes in due course, there'll be a way to actually extract this from this data. And the really exciting thing from my perspective is that this is the data that we have built. All of these products that you've seen in Australia from is available globally, and it's available freely globally due to the great work of GEO, the Group on Earth Observations, who have not only enabled the US access to Landsat, but have also worked with the European Commission to enable the Copernicus data and the Sentinel data to be made freely available to the globe. So everything you have seen in this presentation from the Australian continent is potentially applicable to your own country, because this data exists globally and it exists freely. And CEOS, the Committee on Earth Observing Satellites, has been working with us to open the Open Data Cube code base to make it accessible to every country that wishes to replicate what we've done in Australia for their own country. We've made that data, made that source code available so that people can actually get started and actually generate that kind of capability for themselves. Just to show you that I'm not lying, here's some examples of what we've done with some of the international cubes. This was just an example of a mini data cube that we set up over Hyderabad in India, looking at this dam. This is a Singer Dam just outside of Hyderabad, and what you'll see here is an animation of how that dam over time shrinks and swells. And while there's always water in there, sometimes there's not very much water and sometimes there's a lot. We ran the data cube code over this area and generated a water observations from space view of that area. So you could then readily see when there was no water and when there was water over a 30-year period for that location. That was the job of a few hours to pull together. So you can see how powerful and easy it is to actually turn or to replicate this capability for your own region. Another example, which is one done by Brian Kilo, who I think's on the line listening to this, which was in the Lake Chad area. So Lake Chad is shrinking, it's a major water source for a large community in Chad, Nigeria, and Cameroon, but it has been shrinking very rapidly over the last few years. So Brian used the data cube to run water observations from space algorithm over Lake Chad. And what you can see here is very clearly a step change that occurs on a regular basis in Lake Chad, where you have a drought for a period, but it doesn't recover, right? So it shrinks and that changes the dynamic, and until the next step change, it shrinks again. It's a one-way ticket, and it's a big concern for the millions of people who rely on that for water. But the data cube capability can allow you to not only see what's happening today, it can allow you to see what's happened for the last 30 years, and it gives you a monitoring capability to look forward into the future, because all of this free and open data can be fed straight into the data cube, be updated routinely, and with things like the Sentinel-2 satellite, you can do this at 10-metre resolution every 5 days. Okay, I'm nearly finished now. I just wanted to mention how there is a growing network of these open data cubes popping up all around the world. So CEOS has been doing a great job with Brian in the lead, actually getting exemplars of how easy it is to get this up and running in different countries. So Colombia has an active data cube. Vietnam, there's a data cube being developed for that at the moment. And Switzerland has been very active as well, developing a data cube for Switzerland. And they recently released a couple of products, a detailed mosaic of Landsat data for Switzerland for 2016, and a normalised snow cover index that was generated also from the data cube. Now, we don't have there aren't many areas of Australia that need a snow index, but I'm betting there's quite a few globally. This is an example of how, as a community, we're able to develop these products and share them amongst the Open Data Cube community to develop new tools that everyone can apply. So there's a growing network of compatible Open Data Cubes, which are shown here. They're all using the same Open Data Cube code base, and I really encourage you, if you're interested in this kind of capability for your own country, to visit the Open Data Cube website, which I'll put a slide up to show you in due course. And we're very keen to see these grow, because the capabilities are so powerful that it's something that every country should have access to. So I'm just going to leave you with a little video. It's only a minute or so, that explains the Open Data Cube implementation in Australia that we call Digital Earth Australia. And let me just highlight the difference between the Data Cube, which is the code, and Digital Earth Australia, which is Australia has actually made an investment to turn this into an operational capability, where not only will we generate these products on an ad hoc basis, but we will be generating them every day, every week, consistently, so that the industry can rely on them, so that farmers can rely on them, just as they rely on the weather report. And these products that we've generated will be routinely delivered to everyone free of charge in the entire country as a routine service, just like your weather. And let me just play
The
this,
Australian government
video.
is investing in a world-first analysis platform for satellite imagery and other Earth observations. Building on the globally recognised Australian Geoscience Data Cube, Digital Earth Australia will provide a new approach to organising, analysing and storing vast quantities of data. Today, it translates 30 years of Earth observation data into information and insights about the changing Australian landscape and coastline. When fully operational, Digital Earth Australia will provide us with new information for every 10 metres square of Australia every 5 days. Information on issues that affect all Australians: environmental management, population growth, smart cities, coastal change, disaster management, resources, agricultural productivity, food security, and water sustainability. By providing easy access to free and open Earth observation data, Digital Earth Australia will unlock innovation and capability across industry. Digital Earth Australia, big data for a big country.
And just to reiterate, the reason I called this talk Big Data for a Big Planet is because, although what I've shown you is a case study of the application of Open Data Cube to Australia, bear in mind that every single thing you have seen could be done in your own country. The data is already free and open, the code base is already free and open. What it takes is some effort to actually put the two together, but it is entirely tractable for everyone to do exactly what we've done and to benefit from it themselves. So here are the websites, DEA and opendatacube.org. Please go and have a look for yourself, and I'm happy to take any questions.
Thank you, Stuart. Awesome is the word that comes to mind. Head into the questions and answers section. I would like to hand over to a representative of the Eye on Earth Alliance to respond to Stuart. And today's Alliance spokesperson is Craig Hansen. Craig is the Global Director for Food, Forests and Water at the World Resources Institute. Craig speaks to us today from the Washington, DC area of the United States, where it is commute to work time, so opposite end of the day to Stuart.
Great, thank you. Thank you. And first of all, on behalf of the Eye on Earth Alliance, I'd like to extend heartfelt thanks to Stuart for his amazing presentation today, and to your organization, Geoscience Australia, for all the great work that you've been doing. I also want to especially recognize the fact that, as I understand it, this webinar started at something like 11 o'clock in the evening for you. So thank you for literally going to all ends of the earth and all ends of the day for sharing with us the work that you're all doing. I think this, to everyone on the phone and at this webinar, you know, this is a classic example of fulfilling the Eye on Earth vision, right? A world where environment and associated social and economic information is combined with citizen engagement to improve decision making to lead to more sustainable development. I think what we just heard today is a wonderful example of, you know, cross-cutting knowledge exchange and an effort by an esteemed institution to advance the availability, accessibility, and usability of data. I couldn't help but think of three things that struck me from this presentation. One was the free of cost nature of this. Given how important data is to better managing the planet, the fact that Stuart and his team have been able to utilize this information, which has come free, and have made their own investments, yet still turned around and provided a free product to the world, not just to Australia, is hugely valuable, and I believe is part of the vision of working towards the global commons. Secondly, you've created a product here that makes things analysis ready, which is really critical, because great data oftentimes does not come originally in a usable format, and you and your team have made the investment to actually make that possible. And then finally, I mean, there is an investment, right? There's an investment of people and time, of supercomputer infrastructure, et cetera, that Geoscience Australia has actually done to contribute to this work. And so for that, we all give thanks. And I just want to thank you all, the audience here, in your various time zones, for your participation in this knowledge exchange of the Eye on Earth partnership, and look forward to your continued engagement. Back to you, Derek.
Thank you very much, Craig. Thank you for joining us at what is an equally unearthly time of day for yourself over there in DC. Thank you. So without further ado, we have a couple of questions from Sudhir Shrestha. Sudhir, I'm going to open your mic.
Hi, Stuart. This is Sudhir. I'm from Esri, DC office. It's a great work. I just wanted to see. I missed the first before 5 minutes your talk, but just wanted to hear a little bit about like how you're accessing the data. So as a cube, like how you're accessing the data. The big issue that we face is like how we access the data and how we manage those data sets, and if we have our own algorithms that we want to apply, what are the back end to work on it? Or if there is any resource available to take a look at it. Thank you.
Yeah, so thanks very much. That's a great question. The reality, so Craig mentioned this this use of high performance computing. One of the key things that we had to do to do this at a whole of continent scale was to make use of a supercomputing facility. That then allowed us to, and in fact, getting the data into the supercomputing facility was a big challenge. We had to actually physically move the data in cars from our tape archive across to the supercomputer facility and put it onto spinning disk to make it accessible. So if you're going to tackle an entire continent, it is a big task to do this, but the DataCube code base is able to deal with that. Most of the other implementations that you've seen, though, that I mentioned, Colombia, Switzerland, are much smaller than Australia, and they are tractable to be done within a cloud environment. And in fact, most of those implementations have made use of cloud-based satellite imagery from both the USGS and from the European Commission to populate their data. So the DataCube codebase includes ingestion tools that turn your data into analysis-ready state, and then the tools to organise that into what we call a cube, but it's not really a cube. It's a dense temporal stack of those images, and allows the analysis of those. So it's a difficult question because it kind of depends on the scale that you want to do it at, but it's a much bigger task to do a whole continent than it is to do a single country. That said, it is quite tractable given that some of the big computing facilities that exist around the world to do the whole globe in this way if we wanted to.
So, sorry, one more quick question then. So, like, if I want to access the data through any, are you able to access the data through the APIs, and also the second question is, like, once you have the product that you showed, is it possible to share those products as a web, the REST service, REST endpoint, or any web services that the people can utilize?
Yes, so our products, so let me be clear, the data itself we're talking many petabytes of data. We do have web service access to those data, that data directly, that is accessible through a web service, and every product that we generate from the DataCube is delivered as a web service as well. So it can be sucked into your own GIS tools, and made accessible through that. We use OGC web services as to try and be as compatible as possible with every user. But yeah, our intent is that every product that's generated gets delivered not just as a web tool, but as a web service, so that people can pull those into their own tool sets.
Great, thank you, Sudhir, for the question, and Stuart for the answer. The next question, one of the pleasures of organising global webinars is trying to pronounce names. So I think, forgive me if I get this terribly wrong, Panagiotis Elias.
Thank you, you spelled correct. My name is Panagiotis Elias, you may call me Panos. I work for a Greek company that provides smart farming services. I would like to ask a technical question. It's similar to the previous, and how possible is to, how easy or feasible is to integrate data coming not only from satellite images to data cubes, but also from in situ sensors. And this is a challenge we're facing, not only people working in smart farming, but in other sectors for many years. And one way I can understand is to connect with DataCube and use APIs and extract some data. But is it possible to make the whole process in the same environment using DataCube?
So, great question. Conceptually, yes. It's not something that we have yet, nailed in terms. Our focus has been in getting the Earth observation data sets into this form. However, there's nothing conceptually in the DataCube code base that precludes the addition of point data. And I guess the good example that I was able to give during the seminar was the connection of the in situ stream gauge information with the Earth observation based observations. So those kind of connections are absolutely able to be made. It's not something that we're well advanced with at this point, but there's nothing architecturally or conceptually that stops that work from happening. And this is the real power of the Open Data Cube community, is that we have open sourced the code base, and we are encouraging people from all around the world, as they apply Open Data Cube to their own problems and develop add-ons or capabilities that are valuable to other people, to contribute that back into the code base so that everyone can make use of it. So it would be a great opportunity for your company who may wish to, don't need to reinvent the whole wheel, but want to develop a spoke that actually connects to a particular in situ capability to contribute a piece of code that helps that to happen, rather than you having to invent that capacity from scratch.
Great.
Okay.
Thank you, Stuart.
Thank you very much.
Okay, thank you, Pana. Could I give the floor now to John Vian, I think?
My name is John Feigen from the International HGH and Pesticide Association, and we are mostly looking at pesticide waste distributing at every kind of landfills and things like that. And we were just looking, can you just, with your system, identify these places? Some are very big. And also, can you make a link to contaminated land? Like you say, you make a link to contaminated waters. Can you, without any sampling, also having any information about the way the contamination is in the field and in the earth? Is there anything possible? How do you see that?
Okay, that's a great question too. I guess there are always going to be limitations as to what you can measure from a satellite, for example. We've had many people ask us about groundwater, for example. Now, we can't see below the surface of the Earth, but we can see the footprint of these impacts on the vegetation, on the surface of the Earth. So one of the products I didn't demonstrate was some work we're doing right across Northern Australia, using the information about the greenness of vegetation during drought years to map which of our areas the vegetation actually is able to access groundwater. Because if it's actually able to reach under the surface and access the groundwater, it stays green even when the surrounding area is dry. So the quick answer is it will depend on whether there is a signal that can actually be measured, or a proxy for that signal that's able to be measured from either optical or radar-based satellites. So in your example of contamination, if that contamination is having an impact on the vegetation, then you may well see a footprint that's able to be demonstrated. If it's a good example is we've created a bare soil map for Australia, and so we can actually see places where vegetation is struggling to grow over time, and that may be an indicator in your case. But it won't measure every single parameter automatically. You still need to design an algorithm that actually gets at that as close to that parameter as possible, using the available wavelengths of light that you're measuring from satellite. That's not to underplay the opportunity. As I mentioned with that water quality example, we can measure every water body. Now, we can't measure every water quality parameter for every water body because it's only going to measure things that you can see, not invisible things or microscopic things. However, you can measure everywhere. So you're always playing off, do you have a very precise measurement but only in one location, or do you have a less precise measurement everywhere? this is allowing you to make those trade-offs and decisions. And as I said, it may the best power may be combining this with in situ measurement and getting the best of both worlds, but targeting that in situ measurement using the capabilities of the data cube rather than the current approach, which is randomly assigning our sampling strategies.
Thank you, Stuart. Jeffrey Smith. Jeffrey, you had a couple of questions in the list.
Hi, yeah, Jeff Smith here from Spectra Natura, an Earth observation consultancy in the UK. We're working on projects where we're looking to develop into what we call intermediate products based on the analysis-ready data. And I was just wondering, within the Australian Data Cube, is there a mechanism for developers and small startups to get involved, like a kind of a sort of sandpit playground, sandbox type situation where we could try ideas out on the Data Cube?
Yeah, look, that's certainly our intent. We do currently, we're working with a number of developers from the research community and some startups just to explore what sort of environment would suit the private sector, the commercial sector, in terms of a sandbox. But we absolutely intend to build that sandbox API environment in the next 6 months to enable companies like yourself to build, if you like, third-party applications on top of these services. It's worth mentioning, though, that one of the key issues for us, and the reason the Australian government is investing in operationalising Digital Earth Australia, is that to make it useful to the private sector, and make it worth their while to invest in developing such a tool, there's got to be certainty that that product will continue to be generated on a regular basis. Otherwise, you build an application or a tool that's reliant on a piece of information which only gets done on an ad hoc occasion. That's no basis for a good business. So it's really important that people develop these data cubes initially for, to demonstrate what's possible, but then move into a regular delivery of those products in order to enable that kind of economic activity and make use of them.
Great, yes, fully support that. Thanks very much.
And there is one observation from Kilo on the work that they've done in the Data Cube.
Okay, thank you. Yeah, I just wanted to mention that there was a question there about pulling in situ data and other data sets into Data Cube framework. We've done that in the case with GPM rainfall data. So we've been able to cube some GPM rainfall data. We're using that for one of our landslide risk algorithms and doing some testing. So conceivably, as Stuart mentioned, it's completely possible. So if you have data that has spatial dimensions as well as time dimensions, it can certainly be formatted into a Data Cube construct and then used and integrated with other data sets. Another example of a data set that we use that's just a single slice in time would be digital elevation model data. So that we're also using for a number of algorithms where the algorithms query the digital elevation information in order to make some decisions regarding a particular product. Thank you.
Thank you, Brian. So on behalf of the Eye on Earth Alliance, I would like to thank you, the audience, for joining the webinar. We hope you found the webinar useful. Tremendous gratitude to Stuart for not only the time of day, but I mean, this awesome work. I mean, this is absolutely amazing what's being done. So thank you, everyone. Thank you, audience. Thank you, Stuart. And until our next webinar, goodbye. Have a good day all.